Hello, I'm Dane, and this is Dan Explains. There are some simple things people don't think about much because they seem fairly ordinary, like oil and water being unable to mix. It's a so well known fact that they can't mix is used to describe things that don't get along, like it goes together like oil and water. It's a fact of life that seems inconsequential to most people, unless they're trying to keep their green sauce from breaking before it can be eaten. However, this simple effect, which is at most an annoyance for the average person, is actually one of the most important and consequential physical phenomenon. It's critically important for the smallest single-celled organism, all the way to the most complex multi-celled organism, like ourselves. Let me explain why. It's well known that oil and water don't mix. Well, why don't they mix? It comes down to the molecules that the fluid is made out of. Water, as most people are aware, is made out of molecules consisting of one oxygen and two hydrogen. Most oils consist of molecules that contain long chains of carbon and hydrogen that are called hydrocarbon chains. Water molecules are much smaller than the long hydrocarbon chains that make up oils. But that really isn't what makes them different. It's the types of atoms that make up the molecules and where they're placed. I'm not going to go too far into chemistry, but here's a quick explanation. Water molecules have this bent shape, kind of like Mickey Mouse's head. The large oxygen atom is more electronegative than the hydrogen atoms, so it tends to pull the electrons off the hydrogen atoms, creating what's called a dipole moment. Basically, the water molecules become little magnets, with positively charged and negatively charged ends. If these molecules find themselves in a sea of like molecules, they attract each other, creating what's called a polar solvent. Oils, on the other hand, stay stuck together through what's called van der Waals forces, because hydrocarbon chains are very nonpolar. Van der Waals forces are much weaker than polar forces, so the hydrocarbon chains in oils often have to contain many more atoms than the water molecules do in order to stay fluid. When you mix nonpolar and polar fluids, the polar fluids are attracted to each other, to the exclusion of the nonpolar ones. Hence why oil and water readily separate when mixed. Well, what happens when you agitate the mixture in an attempt to get the oil and water to mix? If you have a lot more water than oil, the oil quickly gets corralled by the polar water into round droplets. If an oil droplet is big enough, it can get a water droplet inside of it, which usually gets quickly forced out. The oil then either falls or rises depending on the density of the oil to recombine and create an oil layer. We try to fight this effect when we wash dishes. We add soap. Soap is a special kind of molecule that is like the polar-nonpolar version of Jekyll and Hyde. It has a long nonpolar hydrocarbon chain, but also on one end, it has what's called a polar head. The polar head likes water, while the hydrocarbon chains like oil. When agitated in water, the soap forms small globs known as micelles, with all the hydrocarbon chains facing in and all the polar heads facing out. Oil and other nonpolar grime gets forced into the micelles, which protect them from the polar forces of the water. This makes oil more soluble in water and easier to wash away, which is why soap is so useful for cleaning. This also allows soap to disrupt cell membranes and kill bacteria. The reason why will become clear in a moment. Now remember I mentioned that drops of water can get trapped inside larger drops of oil when agitated. These usually aren't stable. However, if you mix soap with water and agitate it without oil, water trapped inside the soap gets trapped in a shell called a liposome. A liposome has a polar fluid, like water, on the inside, with a fairly stable shell of soap-like molecules around it. These liposomes create an isolated polar environment inside the liposome, kind of like a fluid-filled bag floating in another fluid. The soapy barrier that separates the inside from the outside is called a bilayer, because it's a layer that has a two-layer sandwich-like structure. Anyone who's taken a microbiology class recently might recognize what a liposome looks like. Although inert, the liposome is actually the most fundamental building block for life. That bilayer acts the same as a very simple cell membrane, so liposomes are basically the same thing as a cell, but with all the equipment that's needed to eat, grow, and reproduce. It's theories that life started when just the right molecules ended up inside of liposomes to make the first cells. Unlike the liposomes that form in soapy water, Life uses a molecule known as phospholipids to create the cellular membrane, hence why liposomes are called liposomes. However, the soap molecules can easily disrupt the bilayer membranes of bacteria because they are so similar. The cellular membrane is also much more complicated than those liposomes and contains all sorts of proteins and other molecules to assist in all the functions of the cell. But that's a story for another video. Thank you for watching. If you like this video and other topics ranging from theology to science, please press the like button, subscribe to my channel, and ding the bell to get notified when I post new videos. Also, please support me on Patreon to get extra content and special perks. Link in the description. The more people support me, the more time I can dedicate to making videos like this one. So, until next time, have a great week.